All right, so we've got some critical values now, which is based on our confidence level. Again, when you're to find the critical value, you start with the confidence level you want, which is based on what you're shooting for. You find your amount of uncertainty that you have to allow for based on your confidence level. You cut that in half because, well, half of it's above, half of it's below. And you use a Z table or technology like Desmos or Excel to find the z-score that would give you that region left over. So I've got those values for the big common critical values just spelled out for you here, but you can calculate it for any confidence level you want. So that's our process so far. We're halfway through. Next up, we've got to find what's called the margin of error, which is really just going to tell us how far we have to go away from our findings in our sample to be confident that we pick up the parameter. And this is just a straight calculation. So we've got E, the margin of error, being the product of the critical value, which just look it up on the table or look it up on the Z table if it's one of those weird confidence levels. You then multiply that to the square root of three things. Inside the square root, I've got p hat, which is our best point estimate, which is usually based on the sample proportion. Q hat, which is just the complement of p hat, and then in the sample size. So we just throw in some numbers into this formula and out pops our margin of error. So for this example we had with Bobbert Bobbington running for the mayorship of Nashville, we polled 1,000 people and 550 said they would vote for him. So p hat, our best point estimate, was based on our sample. And our p hat value was 0.55 because 55% said they would vote for him. So p hat's 0.55. That makes q hat, the complement of p hat, be 0.45. So that pops in there. And then finally, we're dividing by 1,000 because that's our sample size. Square root of that multiplied by our critical numbers, which again changes based on our confidence level. And that's how you get E. So I've done that twice here on this slide. I did it once for a confidence level of 90%. That gives us a critical value of 1.645, which again is just the z-score needed to give you that 90% confidence level. And again for a 95% confidence level with a higher z-score. And that gives us two margins of error, one at 90% confidence and the other at 95% confidence. And what this margin tells you is very important. It tells you how far away you would have to go to be appropriately confident that you've picked up the actual value of the population proportion. So if we had the p hat value, if our sample gave us 55%, then we can be 90% confident that the overall population has a proportion of about 52% to 57.5%. And again, we get that by starting with our sample value p hat, our best point estimate, and subtracting the margin and adding it as well. Subtracting it to get the lower bound, adding it to get the upper bound. Again, for the 95%, that was 0.0308, about 3% plus or minus. So I subtract 3% to get about 52%. And I add 3% to get about 58%. So I am 95% confident that somewhere between 52% and 58% is the amount of people in Nashville who would vote for Bobbert. And you'll note that the lower confidence also is a tighter window here. So real quick, and then I got one more slide to show you in this video here. We got different ways of writing our confidence intervals. Personally, I like using the tolerance where I just say, oh, it's p hat, give or take, whatever the margin is. You can do it with inequalities where you sandwich it between the lower and upper bounds. Or if you're hip to interval notation, which is from algebra, you can also use interval notation. And I'm going to end it here. This is all the information so far. See you in the next video.